Welcome to 1007 ICT, 1807 ICT, and 7611 ICT, Computer Systems and Networks. This is Lecture 10, Internetworking. So last time we looked at the data link layer, we looked at addressing, transmission errors, and medium access control, so basically who gets to talk and when. This time we're going to be looking at the network layer. We're looking at addressing, but at the network layer, not at the lower layer. Subnets, address resolution, the idea about connection-oriented versus connection-less connections, routing, and devices for connecting networks. So there's a lot of stuff we're going to go through. The most challenging part is probably the subnetting, so pay a little bit of attention to that when you're reviewing this particular part. I have a few examples to show you sort of how to run through those when we get there. So we're getting an understanding of these things, and in the workshops, again, you'll probably get some access to doing some processing based around some of these things. So the first question you might ask is, well, why would you want to interconnect networks? Often you need to connect one local area network to another network. So for example, your lab should connect to a wider university network. You might want to connect two separate LANs with different protocols, so different kinds of LANs. You might want to separate or connect one corporate division from another one. So for example, there might be a student division and there might be a staff division in terms of the network. And they may have different access rights depending on which group you belong to. And you would like to separate those networks potentially. You might want to connect a local area network to the internet so that you can browse the web, for example. You might also have many users on this local area network, and so you might want to chop the local area network up into sections, and so that you can relieve traffic congestion between those sections. And lastly there, you might want to provide some kind of security wall between the different kinds of users. Again, if you take the example of staff and students, maybe there are some things that students should not be able to see in terms of their marks, for example, so you want to separate those parts based on the network. So when you're connecting networks, that requires some kind of network device to join the two networks, and that means that the packets can be moved or routed from one network to the other. They can find their destination. To do that, you may need to translate different network protocols, so basically the languages that these networks speak may be different, and you may need to route the packets between the networks. So for example, if you're going to go from network A to network B, you need to know how to do that or which path to follow to make that happen. Some example network devices, we'll talk about them in a little bit more detail later, are hubs, switches, bridges, routers, gateway. You may have seen some of these terms before, and some of these terms may be used interchangeably. The definitions may be a little loose for some of these types of devices. It also requires a network-wide protocol that can handle addressing across the entire network. So before, in the last section, I said we're talking to our direct neighbor, so I need to know the name of my neighbor, and that's enough. If I can get it to my neighbor can get it to their neighbor, and so on, so eventually it gets to the endpoint. At this level, at the network level, we need to know how to get a message across the whole network, which means we need to know the name of the machine on the other end of the communication, not just my neighbor. We need to know how to route packets to their destinations. We need to choose which path to take. Well, so far it's been pretty easy. If I want to send a message somewhere, anywhere in the network, I just talk to my neighbor and I send it to them. It's not always the most appropriate if I have many neighbors, right? So somewhere we have to work out how to get the packet from me to the destination. And we need to perform end-to-end error handling. Now that doesn't necessarily happen here, but at some level, before I can check, like the lower levels, I can check between me and my neighbor. If a problem happens there, we can deal with it directly, right? I'm talking to someone and they didn't hear something I said, so I'll repeat it. That's just between me and my neighbor, but in terms of me and the endpoint, there are potential problems that can happen in between the network connection, so inside those computers. So we need to deal with that at a different layer, in the transport layer actually. So when we're connecting local area networks, you need to consider a number of things: the frame format, the payload size, the data rate, and the address bit order. Some of those we have seen already. The frame format, well, every local area network protocol will have its own idea about what a frame looks like. And that means some conversion will be necessary if you're talking to different kinds of networks. The payload size. Again, every local area network will have a different idea about what is the biggest packet you can have, or the biggest frame, and the smallest frame. And so because that size varies, that means you might need to chop up your frame, or you might need to add stuff to the end of it to make it bigger. Either way, you might have to do. The data rate. Some local area networks are faster than others, which means we might need to slow things down or speed things up, or buffer things, or store things somewhere for a little while so that they can be used later. The address bit order, we talked about that before as well. Do you remember the little endian and big endian problem we had? We have a similar problem here. If your idea of how an address is represented is different from my idea, we have to convert that address. So the network layer is responsible for getting an individual packet, so not the whole message, but just one packet from that message, from the source computer to the destination computer. That's not my neighbor necessarily, it's someone much further away. That means it might have to go through many machines to get there. So the responsibilities of the network layer, and this is the IP part of the TCP IP model, are logical addressing and routing. So logical addressing translate the source and destination addresses into ones that can be understood across all connected networks. Now what that's really saying is, if I talk about a particular machine, we must agree on that machine's name across the whole network. It must be a unique name that I can use, that if I mention it to anyone else, they will know who I mean and how to get there. Does that make sense? So this is like when you put an address on an envelope in the mail, right? The postman looks at it and they can work out based on that unique address where it needs to go. It's a similar idea. Now we call those IP addresses at this level. Right, so you may have seen those before. Routing, determine which path to take from the source to the destination. Now that's most important when there are multiple possible routes between the different machines. So here's an example of that. If I'm machine A over on this side here, right, and I want to send something to E. Well, previously, before this layer, what I said was I'll just send it to my neighbor, right? And then eventually they'll deal with it. So my neighbor will have to decide, okay, I'll send it to here. That neighbor will decide, I'll send it to there. So what we have completed here is a route from A to E. Is that the only route between A to E in this network? Not even close. There are many routes. So sometimes I might choose this one. Sometimes I might choose this one. It really just depends on some of the factors that I might consider when I'm considering the route. So it might be speed. It might be cost. Some of these links may be like toll roads. They may cost me more than some other links. Does that make sense too? Okay, so it really just depends on the particular layout or setup of this network, which route or which path I'm going to take. Here is the TCP IP network layer part, the IP part. The IP or Internetwork protocol is an unreliable connectionless protocol. We'll talk about that a little bit later. The packets in this layer are called datagrams and have the following format, and this is for IPv4, so there's other versions of this. You'll see in the box on the left, there's a bunch of stuff in there, right? We're not really that interested in the stuff at this level. If you look at more detail into IP, you will be interested in this stuff. But for us at the moment, we just be aware that there is a bunch of stuff in there, and it has to do with things like the source IP address, the destination IP address. There's a header checksum, there's a total length, there's the protocol, the time to live. All these things are going to be important when you're sending a message through the network. Some part of that network processing will use that information. Where does it go? Well, you see on the right, the datagram format is the blue stuff is the data, and on the front of it is the header. And the header is that big box that you've got there. So that's for IPv4. IPv6 is the standard that we're moving towards. Probably you're using it in some sense. Maybe it's not completely there yet. So one of the problems with IPv4 is that we ran out of addresses. Right, so we had limited addresses, so IPv6 solves that problem. If you look at the header for IPv6, it's a lot simpler. There's a lot less stuff there. Does that also make sense? Right, so you'll also probably notice that the source IP address and the destination IP address, those boxes look a lot bigger than the previous model. And so we have a lot more addresses to choose from. And so we are transitioning to IPv6 fairly slowly, actually, but it will happen at some point. In terms of network addressing, I mentioned addresses at a couple of different layers already, but in order for messages to get to the correct destination, you have to specify the correct address. It depends on which layer you're talking about, which address you should use. So there are three main levels of addressing in a TCP IP network. Now the first one, the application layer, which is the one we use typically when you're using a web browser, for example, or an email client, it will be something in English like www.griffith.edu.au. That's easy for people. Machine doesn't really like those particular representations. It's not as convenient for it, but it can deal with it and translate them. The network layer, the one below that, TCP/IP, uses IP addresses, and that www.griffith.edu may translate to 132.234.112.9, for example. That's an IP address. It has four groups of numbers between 0 and 255 and a dot in between them. Okay, so we'll talk about that in a lot more detail in a little minute. The next layer below that, the data link layer, this is when you're on something like a network like Ethernet, for example. And at that layer, you don't use IP addresses, right, to communicate. You talk to people on your local network, and you need to know the address of their network card, for example. And so that might be a MAC address in this particular example. And a MAC address has 6 of these hexadecimal groupings with a dash in between them. Can you see that they look quite different from each other? Yeah, so depending on which layer you're working out, you will use a different address. IPv4 addresses. So in TCP/IP, the network layer address is called the IP address. There's 5 classes of address, and they're designed or defined to cater for the needs of different organizations. Now, we found out by now that we have run out of these addresses, so we are transitioning away from this model, but it has been pretty useful for quite a while. Okay, so probably before I get into that part, I'll just talk a little bit about these classes. So you'll see on the left, there are classes A, B, C, D, and E. Now we're just going to focus on A, B, and C for this particular lecture, but there are 5 of them. Class A, you'll notice that there's a blue box and a purple kind of box. The blue box is the network ID, so the name of the network or the number of the network, and the purple box is the host ID, so the name or the number of the host. The network is the thing that you connect to. The host are the machines on that network. Okay, so you'll notice in the Class A, there's a small blue box and a really big purple box. Class B, there's a bigger blue box and an equal sized purple box. Class C, there's a really big blue box and a very small purple box. That means that as you go down the classes, Class A has very few networks, but they have a lot of machines on them. Class B, half-half. Lots of networks, lots of machines. Class C, a lot of networks, and each network only has very few machines on it. That's how it's organized. Okay, so the way that's actually organized is, if you look at this in terms of the network, and this is the host, we have Class A has 8 bits for the network and 24 bits for the hosts. Class B has 8 and 8, or 16, and 8 and 8 for the host part. Class C has 8, 8, 8 for the network, and then just 8 for the host. So that means for a Class C network, you can have 0 to 255 machines on that particular network. That's not a very big network, but it's pretty good for things like our labs and those kinds of environments, right? Whereas for a Class B network, you can have 16 bits, so 2 to the 16, which is 65536 different hosts. That's a very big network. On the Class A network, this is an enormous network. It has 2 to the 24, right, different hosts or different machines. That's 65536 times 2 times 2 times 2 times 2 times 2, right? So double it a number of times. You're going to get a very big number. And that's how these are organized. So what that table down the bottom shows you is the number of machines per network or per class in this network class in this example. You'll see that the top one is a Class B address. Now apparently it's Class B because it's got 2 blue boxes and 2 yellow boxes in this particular diagram. And the example that it's there is 130.11.3.31. So you should be able to look at that number and determine if it's a Class A, B, or a C network. And I'll show you how you do that in a second. There's a group of these pretty detailed diagrams, and I'm just going to go through them as a drawing before I go through these. So I just want to show you there's Class A, Class B, and Class C. So when you're reviewing this lecture, what I'd like you to do is look at these specific detailed diagrams, but I'm going to go through the thinking behind it in the drawings now, just to keep it a bit more simple. So Class A. Okay, Class A, the way it works is it's 8 bits, and the first bit is a 0. So if you have the first bit of a 0, and then there are 7 bits, that means that they could have 3, 4, 5, 6, 7 zeros, all the way to 1, 2, 3, 4, 5, 6, 7 ones. Does that make sense? So you can have O followed by 7 zeros, O followed by 6 zeros and a 1, O 6 zeros, sorry, 5 zeros, 1 0, and so on, all the way to an O followed by 7 ones. So that range will be 0, so this is 0, and this is 127. Okay, the reason that's 127 is this is the 128's column. It's 0, and all the ones to the right are on, so it's 1 less than 128, which would be 127. So the range for the A networks, the first digit can be 0 to 127, which gives you potentially 128 different networks for Class A. Does that make sense? Okay. Now we want them to be separate networks, so that means Class B ideally would start at 128 and would go to another number. Does that make sense too? So there should be no overlap. So B, to make that happen, you would start with a 1 here and a 0 for the second bit, and then you can have 6 bits, so there could be 6 zeros all the way to 6 ones. Does that make sense? So that range will be 128, so 1 with 7 zeros after it is 128, and then 1 with a 0 and then 6 ones will be 191 if you add them up. So the Class B will go from 128 to 191. Is that distinct from the Class A network? Yeah, Class A goes from 0 to 127, and the way we've set this up, Class B goes from 128 to 191. Where do you think Class C starts? 192, the next possible number, right? So how do we achieve that? Well, we put a 1 in the first digit, a 1 in the second digit, and a 0 in the third digit. So this is 128 plus 64 is 192. And if the rest 5 bits are zeros, what does that mean? This is 192, yep. And what is if they're all ones? So 5 ones will be 31. 192 plus 31 is 223. Can you see how we can separate out the classes of addresses just by doing this? And so we're just being clever with where we're putting the bits. But basically we can determine just by looking at the first number, my first 8 bits, what kind of class of address I've got. So if I've got an address which is 146, which class is it? It's a B address because it's in this range. What about 209? It's a Class C address. So just looking at these, it's very easy for me to work out which class it is. Okay, that's the first part. So what I wanted to discuss with these examples is this picture and the next 2 pages show exactly what I just mentioned to you, just in a bit more detail. So this is really useful when you're reviewing this stuff at home or in the recording. They just have a look at how this is laid out, but basically that diagram is the thing that you're looking at here. So that's for Class A, for Class B, and Class C. So next, we run into a problem of we've run out of network addresses actually, right? So we're still working with IPv4, so we found some solutions to it, and one of the solutions is to subdivide our networks. You saw that a Class A address, right? A Class A address has 2 to the 24 machines possibly hanging off each network. Do you know any networks that have 2 to the 24 machines on them? No. Most networks that you're aware of probably have 50, 100 computers on them. Does that make sense? So are we wasting a lot of space with those particular networks if you have potentially 2 to the 24 machines and you're only using 50? You're spending wasting a lot of space. So what you could do is you could subdivide that network class into smaller chunks, and that's what we're going to talk about with subnetworks. So subnetworks are a method of splitting an allocated IP network address into smaller portions, and those portions are identified by a subnet number. So we're not going to change anything on the outside. We're just going to do an internal thing, right, to make it appear to us like we have different networks. And that means that an organization can create multiple networks within their allocated network. So if I have a Class B network, then I can make it smaller, subdivided, and actually have, say, 20 or 50 or 100 Class B networks, depending on how I organize it. Does that make sense? Okay. So the subnet needs something called a subnet mask. So if you've done any kind of configuration, IP configuration on your computer, you would have seen you put an IP address in and then a subnet mask. Has anyone done that in their configuration panels. Most people have already seen that somewhere. So the subnet mask is the thing that identifies which part of the number that you're putting in is the network and which part is the computer. All right, so which part is the network and which part is the host, using the same terminology. So where its subnet number begins or ends and the host number begins. So a mask is a 32-bit word for our purposes that has a 1 for all the bits that indicate the subnet and a 0 for all the bits that designate the host. Okay, so I'll show you some examples in a minute, but basically where you're going to use a series of 1s and 0s, a big long string of those, and the 1s will show us where the network is and the 0s will show us where the machine is. Okay, so the mask is ANDed with the IP address to get the subnet number. So there's a mask example. Again, I'm just going to draw this one. I think it's a lot easier just to talk about masks simply, I guess. So here, if we look at the mask, if these are all zeros and I AND these together, what am I going to get? 1 and 0 is 0. So wherever there's a 0 with an AND, the answer is 0. So I started with 129 and I turned everything off in my mask. All these are zeros. Did any of my initial values get through? No, they all became 0. What about down the bottom here? I make them all 1s. 1 and 1 is 0, 0, 0, 0, 0, and 1. Is this number the same as that one? Yeah. So what it lets me do with this mask, if I put 1s, the number above falls through. Get the same number, same value, right? If I put 0s, I block off some parts. Okay, so I can selectively turn on or off parts of my number. So with a mask of this is 255, I let everything through. Does that make sense? And if you've done any of this IP stuff when you configure something in one of those little windows, if you have a mask 255.255 point something, right, that's what you're doing. You're letting certain parts through. So let's have a look at a smaller example. So instead of having everything on, I've only got this part on. Does that make sense? Only these 4 are on and these 4 are off. So I'll do the AND. 1 and 0 is 0, 0, 0, 0, 1, 0, 1, 1. Which part went through? This part, this left hand part. So I can, again, like I said, selectively turn on or off this part. And what I do in my later examples, this will be the network part and this will be the host part. Does that make sense? Yeah, I just only choose the left hand side for the network and the right hand side for the host. Okay, so that's the same example I went through there, just with showing you what a mask is. Now here's an example. Given a class C IP address, 192.2.3.130, how do we determine the network ID and the host ID? There is an example here, right? I'm just going to walk through it now on the diagram, just to show you how this kind of works. So it's a class C address. I can tell because it's 192 point something. That puts it in the class C range. Class C addresses have 3 bytes for the network. The first 24 bits are the network part. That means I want to keep them, which means that my mask will have 8 ones. 8 ones is 16 ones, and 8 ones is 24 ones. Does that make sense? Yep. If I look at this as a number, what number is this? This is the number 255. 255, 255. And this is 0. The last 8 bits will be the host part because this is a class C address. First 3 lots of 8 are the network, the last 8 is the host. So my mask is 255.255.255.0. That's this line here. 24 ones, 8 zeros. What does that do? Well, let's look at the zeros first. These are all zeros, right? So what do they let through? Nothing. These will be 0, 0, 0, 0, 0, right? 8 zeros. Does that make sense? So that's my host part. So that means that the remaining part in red here is the network part. And because these are all ones, what gets pushed through? Whatever these ones were. Does that make sense too? So if this is 192.2.3, what do we end up with? 192.2.3. 3.0. So the 0.0 on the end indicates that this is the network. Okay? Let's look at the other side of this. Imagine that I don't want the network, but I want the host. How do I achieve that? Well, where is the host in my class C address? It's at the end. So I turn on the last 8 bits with my mask, and I turn off the first 24 bits. I don't want the network, I want the host part. So my mask in this case would be 0.0.0.255. I'll just point out that you don't usually use this kind of mask. You won't see this very often, but this is what you could do to get the host part. So if you did that, you don't let any of this through, so this becomes 0.0.0, and whatever was here, this is 128 plus 2 is 130. The 130 gets pushed through. So this is host 130. Yep, and we don't care about the network part. Is this pretty simple in terms of the mechanism? What do you think? Yeah, the mechanism's okay. Just the processing may be a little bit new and a little bit tricky, but the idea is very simple. Whatever you want to leave through, you put ones in your mask. Whatever you don't want, you put zeros in the mask. And typically, there'll be a row of ones from the left to the right until you want the host, and then there's a row of zeros. Okay. So that is a class class C address. A class B network. So an example organization has a class B network. They have created 256 subnets using the third byte to denote the subnet number. Each subnet has 256 hosts. So now we've got a class B address, but we have subnets. Class B addresses, how many bytes do we use for the class B part? Oops, excuse me. How many bytes do we use for the class B part in this example here? Class B, how many bytes? Class A, 1 byte for the network, 3 bytes for the host. Class B, 2 bytes for the network, 2 bytes for the host. So normally we would have 2 bytes for the network, 2 bytes for the host. If you look at the setup here, the mask to get the subnet ID is not 2 bytes, but it's 3 bytes. Why is it 3 bytes? Because we're using the third byte to represent our subnets. So the normal network will be the class B network, that's the first 2 bytes, and then our subnet is the next 8 bits, or the next byte. And so if we want the subnet, we need the mask to cover all the first 16 bits, plus our 8 bits for the network, the subnet part. You notice the last part is again the sequence of zeros because we don't want the machine, we just want the subnet part. Okay, so showing you a slightly different example, going back a step, in terms of the class B network, class B, 129.6.7.3. So 129.6, if I want the class B part, how do I do that? I just want the network part. What do I need to do? I need a mask, and which parts of my mask should be on? It's class B. How many bytes? First 2. So the first 2 are on. Does that make sense? Yep. Okay, class B. Now that means that the rest of this is off because I don't want the machine part. I don't want the machines on this network. So what is my network? It's 129.6.0.0. Now you'll notice for a class B network, if I have a lab with only 25 computers, then this byte here should be plenty to capture that. Does that make sense? I'm wasting a lot of space here with my network. Does that make sense? So what we're suggesting is that we can use this byte as a subnet, and maybe I have 255 subnetworks, and each subnetwork can have 255 computers on it. If I want to achieve that, what do I need to do? I need to use this set of bits as part of my subnet, and that means I shouldn't have them as zeros. What should I do? They should be ones to let through this part, which is 0.7. That means that this is subnetwork 7, yeah? And which machine on subnetwork 7? Machine number 3. How do I find out which machine it is? Well, if I'm just using a Class B network, what I would do is I would turn off the network part and I would turn on the host part. This is if I'm using 16 bits for the hosts. Yep. So the machine in this case would be 7.3. Does that make sense? Yeah. But what if I'm using this series of bits for my subnetwork? They would then become zeros. So what machine do I have? Machine number 3. This is machine number 3, and looking at my previous diagram, this is network number or subnetwork number 7 inside the Class B address 129.6. Does that make sense? Is it a little bit tricky? It's a little bit tricky probably, right? So subnetting is not necessarily the easiest thing when you first see it, but it's very regular. So once you get the basic principle, right, that you're subdividing a network into smaller chunks, it'll become a little bit easier. Okay, so there is another example here for a Class C subnetwork. Okay, the Class C subnetwork, this one is a bit different. I'm going to leave this example here so you can follow through this one on your own. I'll show you a slightly different example to work through, all right, so you can have 2 examples showing you how to do it. This one, Class C network, they've created 8 subnets using only the first 3 bits of the last byte. So in a Class C network, you have 24 bits for the network and then only 8 bits for the host. That means you don't have many bits left, only 8, to do these subnets, right? So you can't use many bits for the subnet. So we're going to use the first 3 of the last 8 for the subnet. That's what this example will show you. So let's have a look at this one. So if I'm using a Class C network, it's 193, that's a Class C network, we can tell that, and 193.6.7 is the Class C part. That means I will turn on this one, and this one for my mask, and really I should turn all of these 8 off. Is that correct? Normally for a Class C network. But what we said was, look, we want to subdivide our Class C network and we want to use the first 3 bits of the last 8 group as our subnetwork. Now what that means is I not only have to turn these ones on, but also the first 3 bits to get my subnetwork. Okay, so what do? Well, 193 falls through here, 0.6 falls through here, 0.7 falls through here, and then part of this falls through, and not all of it. So which part falls through? 110. What's 1 here? This is 128, and what's the next one? 64. 128 plus 64 is 192. Does any of this fall through? No. So it's just 128 plus 64. So my subnet is 192 in this case. Right? You see how I generated that? Might not be that meaningful at the moment, but his subnetwork number is 192. So basically what I've done here is I have turned on my normal Class C subnetwork bits. There are 24 of them. That's the first part. And then the scheme they told us was we only have 8 bits here. We want to use the first 3 for the subnetwork. So if I use the first 3 bits, I'll turn them on. I'll turn everything else off, which means nothing else goes through, which means what comes through is 110 and 5 zeros. Is that correct? Yep. So if I add these up, 128 plus 64 is 192. So my subnetwork is 193.6.7.192. Now, that's the network part. What about the host part? So the host part is a Class C address. I will turn off all of these 24 bits, and also we're using the first 3 bits for the subnetwork, so I'll turn those off. So what I'm going to get through is 000-00101. Yep. And this is the number 5, which means the host is 0.0.5 on network 139.6.7.192. Can you see I can still chop them in half like that? It's a little more tricky just looking at how that works, but that's basically what we're doing. So what I've got here on this page is another example for a Class C network. So with that same setup, different numbers, you can have a look at it and compare it to what I just went through on that diagram, and then you can see the similarity or the difference. So I invite you to walk through that one on your own and just try that one out. So putting that together as a subnetworking example, just as a diagram, let's just draw this, you've got an incoming address, 132.5.4.96. What kind of address is that? Class A, B, or C? It's a class B address because it's in the range 128 to 191. Right? That's what we worked at before. Now, if it's a class B address, that means that the normal scheme is the first 2 bytes are the network, the second 2 bytes are the host. We are subdividing that. So we're subnetting, and we're actually using the 3rd byte as our subnetwork. So let's see how this works visually. So 132.5.4.96 goes into the router. Inside this network, it says, okay, I know that we're subnetting this. So instead of just using the subnet mask 255.255, which is 16 ones, I'm going to use 255.255.255. This is 24 ones, and it captures this one as well, right? The 3rd byte. So when I get inside here, it's 132.5.2 is one subnetwork, 132.5.4 is another subnetwork, 132.5.1 is another subnetwork. Which one am I looking for? Point 4. Is it this one? No. Is it this one? Yes. Right, so I'll go to this one, and when I get to this network, you'll notice that this is 132.5.4.0. That's the network. Which machine do I want? Machine number 96. So I look through my network here. Is it this one? 11, 1, 43. Oh, it's this one, 96. Can you see I can use this networking, first of all, the classes to get there, then the subnetwork to find out which subnetwork it is, and then the host to find out which machine I'm looking for on that network. That's how we sort of subdivide it. We also have something called an address resolution protocol, the ARP. It associates an IP network address with the physical address or the Ethernet address on the network card. So basically what you're going to get is something like a computer saying, look, I'm looking for the physical address, the MAC address of the machine with the particular IP address. And this example is the IP address 141.14.22.1. So someone on my network has that IP address. I don't know who it is. We haven't communicated yet. So I'm going to send out this broadcast and say, if you're this machine, tell me what your MAC address is. And that machine says, oh, okay, that's me, and here is my, so I'm going to flood this out to everyone, and this one says, oh, that's me, and my MAC address is this. So now I have not only the IP address, but the MAC address. So when I get some information for that IP address, I can just send it directly to that MAC address on my local network. All right? Okay. We already saw this diagram before with the switching. So in lots of networks, we don't directly connect things together. We use switches or multi-point routers depending on which level you're looking at. So communication between any two nodes can involve passing through several of these switches. And there's 2 types of switches, 2 main types anyway, circuit switching and packet switching. So circuit switching permits any 2 network devices to talk together at any one time, like the telephone. So this is a connection-oriented model. You have a connection, right? When you're on the telephone, you have the connection until you hang up. Does that make sense too? That's a particular kind of connection. It creates a dedicated physical point-to-point connection to exist between the devices for the duration of the communication. Once you hang up, that connection is terminated. The data travels in a continuous stream of bits, and that's important for a phone call because the things that you say should arrive on the other end in the same sequence that you said them. Otherwise, the language will be messed up. Right? So the advantage of this is that it's secure. It's most suitable for continuous, like streaming or real-time data, like telephone calls. The disadvantages are that it's not very efficient because there's lots of data that doesn't need to end up at the other end in the same sequence that you sent it. It's important for a phone call, right, because you need to understand the other person. And that's what this looks like. This is a circuit switched network. So here, on the top, circuit switch network, let's look at the top one, you have this machine sending packets, and those packets go in the sequence that you sent them, and it goes directly to that one. This one here, the red one, wants to talk, but the phone line's busy. Have you ever had that? You try and call someone and the line's busy? You can only accept one connection at a time, right? So that makes sense. You have a continuous connection. There's one of those. If you move on to the packet switching model instead, then a device can simultaneously connect to any number of other devices. It's not just one phone call, and it can either be connection-oriented or connectionless. So we'll talk about the two different models. But the basic idea here is that you chop the data up into these packets, and you can move the packets around any way you want. They don't have to go the same direction every time. So the advantage of this, it's more efficient for typical computer data. If you're sending a spreadsheet, does it matter if the information is sent across the network in exactly the same order that you have it in the spreadsheet? It doesn't matter as long as at the other end it's reconstituted in the right way. Does that make sense? So it could go all sorts of pathways. It doesn't really matter. The disadvantage is because it's going everywhere, it's harder to secure and it's less suitable for continuous data. If you did that with a phone call, you're going to get garbled messages because some of the packets will arrive out of sequence, right? So this diagram here, if you look at this model, you'll see that the link in the middle is shared by packets from different devices. So this guy's sending something, this one's sending something, and they're just shared in the middle here. And when they get to this switch, it says, okay, the green ones go this way, the red ones go that way. And on this end, you may regroup them in some way. So types of packet switching. So we mentioned there are two types. So the connectionless and connection-oriented. So each packet for connectionless, the datagram model, travels independently through the network. There's no error control. If you lose something or you get it wrong, you just throw it away. It's called an unreliable or a best try service. This is an example of this is the IP model. This is the kind of model you have with streaming, right? If you're sending or streaming something, do you care if you miss a packet? No, the stream doesn't look that great for like a second or half a second, like the screen glitches or the audio doesn't sound great, but the thing continues, right? You're watching a video, for example, that's fine. Does that make sense? Connection-oriented, the virtual circuit model. A logical connection is established between the source and the destination before any packets are sent. The packets from a single message travel along the same path, and that logical connection is called a virtual circuit. It's not a real circuit, it's a virtual one. It doesn't actually exist. And once a single pathway exists for acknowledgements to be made, you can do error checking and flow control. So if you want to have those features, you would want to use the virtual circuit model rather than the connectionless or the datagram model. Right, okay, so depending on what you want to achieve, you will use one or the other. Same sort of question in terms of streaming. Do you really care if you drop a frame here and there for streaming? Not really. So is the error checking necessary for that? Probably not, right? So maybe you need it for some things, but mostly you don't really care. So depending on the application, you may choose one or the other. So here's a diagram just showing you the two different models side by side. So connectionless datagrams up at the top here. So this one's sending lots of packets. 3 and 4 go this way, 1 and 2 go this way, 4 goes this way, 3 goes this way, 1, 2, and 4, and eventually 3, 1, 2, 4 ends up over here. So if you get this, you're going to have to reorder these because they're in the wrong order. Does that make sense? That's just a virtue of how they're going through the network. Some of them will arrive faster or slower than others. The connection-oriented, the virtual circuit one, well, I'm sending 1 and 2. 1 and 2 go this way, 1 and 2 go this way, 1 and 2 go this way. They end up at the destination always using the same blue path here. They end up in the same order at the destination. Is that a different model to the one up the top? Yeah, and you might prefer one over the other depending on what you're trying to achieve. So just as a diagram to put those together, particularly because there are two connection-oriented terms here, if you're looking at switching, there are two broad categories. You have circuit switching. Circuit switching is connection-oriented. This is like the telephone model. You also have packet switching. Packet switching has two flavors, connection-oriented and connectionless. Right? So those are the two diagrams I just showed you just then. And the difference between the packet switching model there is that the packet switching model chops things up into smaller packets. Right? So you send them across the network. So another thing that happens across the network is routing. So routing is the process of determining the route of the path through the network that a message will travel in order to get from the sender to the receiver. Basically just the path that you're taking. The paths are selected by switching the packets on the correct links at each node, and every computer on the network will have some kind of routing table to work out if I get a packet and it's meant for this particular machine, which connection should it go out of. So there's a routing table here, and you'll notice that we're looking for node B here. So this is node B's routing table. Every node will have their own routing table, and node B says if I want to get to A is over here, I should go out the link going to A. If I want to go to C, C is over here, I should go to the link going to C. They're directly connected. That's very easy. If I want to go to D, where's D? D is here. Can I directly connect to it? No, that means I have to choose another link, and I have chosen to go out through A. Could I also have chosen E? Sure, I could have chosen C if I wanted to, depending on whether A is faster or B is faster or E is faster, whichever. So you'll notice that if I want to get to E, for example, I'll just go directly to E. If I want to go to F, I'll go through E in this case. And so I can get to every other node, not necessarily directly, but maybe I know a neighbor who can get there from where I am. And that's a routing table which every node will have in that network. So the goal is to select the most efficient paths through the nodes. Lots of different reasons why you might choose a particular path. It might be that there's lower delay, there are smaller number of hops or number of steps you have to go through. Maybe the machines are more powerful on this path, they can do more processing. The link capacity is bigger, maybe you're using fiber on one and a dial-up on the other one, you want to use the fiber side. Sometimes the different switches and links may be overloaded, so you might route around them. It's like a traffic kind of environment, right? If a road is really busy, you're not going to take that road, less likely you're going to go around. Latency, so there may be some delays in some parts and you want to avoid those. And some desirable properties for routing would be correctness, you have to get to the right place. Robustness, it doesn't fall over very easily. Fairness, it's pretty fair. Simplicity, minimize delay, and maximize the throughput. There's lots of different approaches to routing, different algorithms. The first one is easy. You always take the same path. That's a little bit problematic if things break. So another one is random. You just send it out randomly. That doesn't seem that good, but on average, if you're sending it actually randomly, then maybe it's not so bad. Broadcasting sends the packet on all possible paths. That's very, very expensive. You tend to overload the network if you do that, but it will get there very quickly if the network's not overloaded. And dynamic or adaptive would probably be the most appropriate one, where as the network changes and this part becomes busy, you work your way around it. This is what we do in the real world in terms of the traffic, right? If something is busy on a particular part, you will find another pathway around it. Network devices, so different devices you use to switch or route a packet from one host or a network to another. They may need to do some translation between the protocols. They may need to route the packets as well. They may need to do a lot of different jobs. Some example network devices are hubs, switches, bridges, routers, and gateways. We mentioned them at the start. So different devices are needed to connect different types of networks. Switches can be used to interconnect segments of a local area network. Local area network to local area network connections are often performed with some kind of bridge-like device. Local area network to wide area connections are usually performed with a router or a gateway. So this is kind of like your home network. You've got a home local area network. You're connected to an ISP, right? And usually there's a router or something in between you and your ISP network. And repeaters, you may or may not have these at home, but basically if you need to extend a signal, you might use a repeater to do that. It doesn't change the signal, it just boosts it up. So repeaters and hubs are physical layer things. They basically just regenerate the signals, and hubs can be considered to be multi-point repeaters. So basically a hub takes in a signal and it just propagates it out the ports to all the other different machines connected to it. Switches operate at the data link layer, so we're moving up. They connect different segments of a single local area network together or interconnect two or more workstations. Workstations that connect to a switch each use dedicated point-to-point segments. And what that basically means is if you've got multiple users on a network, then you can separate them through the switch. You can have this user on this side of the switch and this other user on the other side of the switch, and they don't interfere with each other. So when a packet arrives at a switch, the switch examines the destination address and forwards the frame through the appropriate connection. So it can choose. It might have 10 different connections. It says, okay, you come in on this one and you want to go to this machine. That machine is attached to this connection. I'm going to send you through that particular connection only. It puts you through one connection rather than the hub, which sends you through everyone. This diagram here shows you the hub at the top. The hub has one piece of information coming in and it transmits it out of all the ports to everyone else. As opposed to the switch down the bottom, you'll see the switch has 4 machines attached to it, and there are 2 sets of communication. There's a red communication on the left and the red communication on the right. Right? That means that the 2 machines on the left are communicating directly, and they're not interfered by with the machines on the right. Does that make sense? Okay. And so the capacity of the switch is going to be much higher in terms of the throughput than the hub. Bridges. A bridge or a bridge-like device operates at the data link layer and can be used to connect two similar local area networks. A bridge could be used to connect a CSMA-CD local area network and a CSMA-CA wireless local area network. The problem with a bridge wouldn't be that they buffer all the frames before they forward them. That means they introduce a delay, and also this bridge can overflow or overload, right? So if you have a lot of communication and the bridge is not fast enough, because it has to buffer everything before it translates it, it will run out of memory at some point, right? So that's not a good outcome. Routers and gateways. Routers operate at the network layer. They can determine which is the best path for a message to take between networks. You have a router at home most likely, right? How many options do you have for the path leaving your home to the ISP? Typically one, right? So it's really easy. But that's not always the case. Maybe you have multiple options in some environments. So you can determine the best path. A router can be a special purpose black box or a computer with several network interface cards or a special network software module within a computer. So it can be lots of different things. It might be a box like you've got at home or maybe something else. In enterprises, the gateway is the computer that routes the traffic from a workstation to the outside network. So you have one machine typically set up that says, okay, I'm taking all the networking stuff that needs to go outside and I'll go through me and I know what to do with that. In homes, the gateway is the device that connects the user to the internet. Here's a picture of some network devices in action. So lots of machines on the right-hand side connected to switches or a wireless router, which is connected to a bridge, which is connected to a switch down the bottom. There's a router right next to that burning wall, the firewall. It's a great picture. And so basically to get out to the internet, you have to go through this router, right? And there's a bunch of machines or network devices attached on the right-hand side. In summary for this section, we cover quite a lot. We looked at the network layer, addressing subnets, and I'd like you to review the subnets in particular, especially if you're interested in doing networking. Subnetting is a big part of doing the networking type major. Address resolution, connection-oriented versus connection-less environments, routing and devices for connecting networks. Next, we will look at the transport layer and internet applications. And that's the end of this section.